Hi everyone, today we are going to discuss very important phenomena in physics, that is the phenomena of superconductivity. In these slides I will going to discuss what is the phenomena of superconductivity and what is its theory. So I will just going through some basics of this phenomena. So first I will discuss what is the superconductivity. Superconductivity is the state of matter with zero resistance and it is perfect diamagnetism. So what does it mean? I can show this in this graph. Certain metals and alloys show this phenomena. So if you decrease the temperature, the resistivity starts decreasing with temperature, but at certain temperature there is a sharp drop in the resistivity, and so that below this temperature the resistivity becomes zero. In this state the materials are perfect conductor, means their resistance is zero and their conductivity is infinite. This temperature below which this happens, this temperature is called transition temperature, or it is also called superconducting transition temperature. Another important thing is perfect diamagnetism. It is also called Meissner effect. If your material is in this state of superconductivity and if you apply the field, then magnetic field lines are expelled from the material. It will never penetrate inside the material. So they behave like a perfect diamagnetism. So superconductivity is not only the zero resistance phenomena, it is also the perfect diamagnetism phenomena. So this zero resistivity and perfect diamagnetism could not be explained by the Maxwell theories. So the first attempt to explain this phenomena is given by the London brothers, and they give two equations. They are called London equation, and their prediction is this very important equation that is called London penetration depth. It is given by this equation. So they show that the inside the materials the magnetic field lines penetrate and they decay exponentially with the distance, and with a characteristic length of lambda, and lambda is very small, that is of the order of nanometer. So that material in the material the magnetic field lines can only penetrate only on the surface. In the bulk of the material the magnetic field lines are zero. Another thing is critical field. This is another important parameter. I mean, there is a certain limit to the applied field below which the superconductivity exists. If the field is above this field, then magnetic field lines penetrate inside the material and superconductivity get lost. So this upper limit to the critical field is called magnetic field is called critical field, and further it is function of temperature. It is given by this graph. Means as the material is at the high temperature, the critical field required to destroy the superconductivity is lower. If the material is at the lower temperature, the critical field required to change the destroy the superconductivity is very high. So the first attempt to explain this phenomena is given by the Bardeen, Cooper and Schrieffer. This is called BCS theory of superconductivity. This is a Hamiltonian of this theory, which is a very complicated one. And the basic idea of the theory is that at sufficient low temperature, electrons near the Fermi surface becomes unstable against the formation of Cooper pairs, and in conventional superconductor the electron lattice interaction is responsible for creating an attractive potential that results in binding of the electron. So the basic idea is that two electrons form a pairs, and the pair is formed by interaction through the phonons. So it is the lattice that participates in binding two electrons, and the pair of electrons is called Cooper pair, and they have the property that their spins are of opposite and their momentum is also opposite. The important prediction of the theory is these following, that is there is a isotropic gaps around the Fermi surface. This superconducting gap is of the order of milli-electron volt. Another thing is exponential temperature dependence of superconducting heat capacity, that below the Tc the heat capacity decreases with temperature exponentially as shown in this graph, and at Tc there is jump in heat capacity, and this amount of jump depends upon the superconducting gap by some appropriate formula that is given by the BCS theory. There is another important thing, that is decrease of gap with increasing temperature. As you increase the temperature, the superconducting gap decreases. It means that you need a less energy to break a Cooper pairs. Another important thing is isotope effect, which says that critical temperature directly proportional to m, where m is the mass of the lattice ion raised to the power minus alpha. So this shows that the lattice actually participates inside this in the phenomena of superconductivity. Thank you. This is all I want to show you in this video. Thanks a lot.